Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, so my name is Walker White. I'm going to talk to you, as you said, about scaling simulations through declarative processing. I work with an interesting group of people at Cornell. We're nominally what you might consider a database group. We work in database technology, but we've been doing a lot of stuff in simulations these days, sort of hybrid technology between simulations and databases, and that's what I'm going to talk to you all about today. So, scientific simulations are really, really important these days, particularly if you're trying to do exploratory research, right? If you're trying to sort of do some visualization of what your scientific models look like, or if you're trying to do some sort of real-time parameter tuning of your models. There are a bunch of application areas for these types of things. However, I'm going to focus on two of these in this talk, in particular because the type of simulations that we're focusing on are agent-based simulations. So if you have a simulation where what you're really trying to do is to solve very complex differential equations, over and over again, the type of thing that you would maybe feed to MATLAB, that's not the type of stuff that we do. The type of stuff that we've been really trying to get a handle on is, so one of the applications areas that we're in is traffic. How do you sort of so in traffic you have intelligent people that are in cars and they make decisions, and how does that control their traffic patterns? Because when you're trying to look at things like greenhouse emissions, energy usage, and the like, you really do have to take into account the intelligence of the people driving these cars in doing your simulations. All right? Now, the problem with doing simulations is that software development's really, really hard. You have these long life cycles, and this is especially true if we want performance, right? We just had the previous person talk to us about, we've got all this great hardware, and you have to do all this hand tuning in order to get performance out of it. The problem is that scientists are not architects, right? They want to do science. And what often happens is, suppose you're a scientist and look, the whole purpose of a simulation is to do visualization of your model. You discover that your model's wrong. You want to go change your model. Great. Go send this to the software engineers, have them redo your architecture. They'll get back to you in a year or something like that. And that's uncool. So what do we do about that? Well, it turns out, and so I'm not going to pull on my other hat here in a second, what we're going to do is we're going to look at ideas from the game industry, because they've actually been solving a lot of these problems already. And in fact, modern games are really very much interactive simulations, right? They simulate physics, they simulate behavior, and one of the things that you've been seeing is that when you go to these game conferences, people interested in simulations, like people in the military, people in scientific simulations, are going to these game companies going, well, what type of technology do you have off the shelf that we can use for our applications? Right? This is very, very common. In fact, it may be gauche to say this at a Microsoft conference, because I know they have axed the flight simulator division, but that was a business decision, not a technological decision, and this is a perfect example of sort of the crossover between entertainment and simulations. Right. So as I said, right, we're looking at games for off-the-shelf solutions. Well, one thing to look at game companies for sort of technology off the shelf, another thing interesting to look at game companies is really how they do their software engineering for their simulations. Because, well, I think that was a joke that I'm just going to skip. So specifically what I'm going to do in this talk is I'm going to look at the very beginning, before I get into scientific simulations, I'm just going to look at what we call simulation games. So simulation games are games where there's most of what the game is doing in its computation is simulating a lot of character behavior in the background. Things like The Sims, right? Most of the time in The Sims, you have all these people on the screen moving about, doing things, and what I can do as a player? Well, I can do things like buy them a piece of furniture, drop it on the screen, but the computer then reacts to that, right? If you drop a refrigerator on the screen, then they go, oh, okay, now I'm hungry, I will go grab something from the refrigerator, and I'm not controlling that at all. Right? The computer is controlling all of that behavior. And there's a lot of really high technology going on in things like The Sims. All right. Real-time strategy games are another thing. I think I will skip that for this audience. All right. Now, as I said, game development's really complicated. And in fact, what happens is that game companies break themselves up and so you have programmers and designers. Programmers are, the types of people who, they make the software, they make the things that make games run, but game companies don't get paid for making a piece of software. They get paid for making content, making for things that actually do things. And so you have the designers that are the people who actually create the game content. They're the people with who sort of know what fun is, and maybe they know a little bit about programming, but they don't know anything about architecture. And all of software engineering and game companies is getting these two people to talk to one another. My, that sounds really familiar, doesn't it? Right? Because, well, suppose we're talking about scientific simulation. Programmers sound a lot like your programming support. And man, that sounds like your scientist, doesn't it? Right? They know, maybe they had a little bit of programming. Yeah, they can use MATLAB. They can use some very standard programming languages. But, oh my God, you've told me that there's a brand new chip out today that I've got to know how to program for? Forget it. Right? That's ridiculous. Right? That's too much to expect of me. So what do we do? Well, actually what happens is that to get around this problem, today's games are entirely data-driven. All game content is separated from the game code. And this happens in many different forms. And the advantage of this is that the engine is reusable. You hire your little software engineers off to the side, they make some game engine, it gets used for about 4 titles, over a span of years, and then you just have designers cranking out new content all the time. And so what happens is that your programmers are this support team, right, that make tools to enable your designers to do their jobs. Wow, wouldn't it be great if we could have this type of thing for scientists, right, doing their simulation? All right. Okay, so I'm going to call these things non-player characters. I'll call them agents here in a bit when we talk about simulations. But in these simulation games, the idea is that I have all these characters that are controlled by the computer. And so all behavior has to be computer controlled. And what's going on is they're acting according to a script. And a script is just a programming language for designers. Something really, really simple. Okay? Now, there's a problem here. And I'm going to use a game example because I could use an example with fish or ants here, but this is sort of a funner example, and it's actually easier to sort of get to the heart of what's going on here. But suppose I have some sort of game, and in the game I have knights and skeletons. And the idea is that knights are afraid of skeletons. But they're not just afraid of a single skeleton, right? This is fairly complex behavior going on here. If it's an army of undead, like if I see a lot of skeletons, right, I'm going to run away in fear. So that means that every single knight has to count every single skeleton. Well, we all know how computers work, right? The way that happens is that each knight goes, are you a skeleton? No, you're not a skeleton. Are you a skeleton? Yes, you're a skeleton. Okay, maybe I'm getting afraid now here, right? And this is really bad because every knight counts every skeleton in his views. So that means that each person counts, up to n skeletons if I've got n people out here on the battlefield. And if I've got up to n knights, that means it's n squared to process all units. This is the n squared problem. This is the major, when everybody interacts with everything else, this is what slows down your simulations. This happens also in scientific simulations as well. In scientific simulations, it gets even worse, right? You can have cubed problems or exponential problems or the like. But this is what slows down, as you can see, right, if it's just 1, but it grows and it's not growing linearly. And this is very, very bad. And game programmers can't live with this at all because their computation has to be about equal to the animation frame rate. Scientists, maybe you could live with something a little slower, but not that much slower, right? If you actually want an interactive simulation, right, something that I can change the models, the parameters to my models in real time, hey, I'd like to have that. You give it to me. How do you do that? All right. Now, the problem that game companies run into, though, is the designers are giving this scripting language, and there's this trade-off between expressiveness versus performance. Game companies are very, very good at coming up with scripting languages that are high performant, but they can't necessarily do a lot, is the problem. Right, so here are a bunch of games, and the idea is that, so in this game down here, Neverwinter Nights 2, I have complete control over every single character in the game, and I can make them to do very, very complex things. But I can only put so many characters on the screen at a time. This game up here has armies of thousands, right? And I'm simulating thousands of people interacting with one another. But it's all fake. What's really going on is the scripting language is controlling 200 people at a time with one brain. And then I'm using like some sort of like particle mechanics or something to simulate them. So you see what I mean by I'm trading expressiveness for performance. When we first started looking at this problem, we said, oh, we want to be here. Doesn't everybody? And how do we do that? All right. And as I said, right, so one of the problems with these scripting languages is, there's problems with performance. There's some lack of support for concurrency. We can get around that a bit. And all that just makes development harder. Is there a way that we can have both scripting and performance? How do we do that? Well, look, database systems are scaled to petabytes. And how do you do that? Well, it's because queries are specified in some sort of declarative language. And what that declarative language is you just say what the type of data that you want, but you don't tell me how you get it. I figure out how you get it, right? And I look at sort of what you're asking for your data patterns, and I optimize to that degree. Wouldn't it be great if you could do that with simulations? You tell me how you want your agents to act, and I'll just do it. You don't tell me, you don't worry about what chip you work on or how you transfer your data or what your performance is. I figure out from your character behavior how to make them fast, how to make them performant, how to work them on any sort of architecture. That's what my goal is here. How do I do that? Okay. So I have given you sort of my motivation talk for why it is that I want to do this. And I'm going to stick with games just a little bit to sort of give you some idea of how games do simulations and how we're going to be able to adapt this to agent-based, and then eventually I'm going to talk about how we adapt this to agent-based simulations in science. All right? All right, so the idea is what's going on in this simulation engine is it's, in some way you can think of it as animation, right? I'm running this one big loop over and over again, all right? And I'm just going to call one go-through of the loop of tick, all right, a tick of my simulation. And the idea is that during each tick, every single agent reads the environment, right? I'm a car in a traffic simulation. Am I about to hit somebody? Who's nearby? Am I coming up to an intersection or something like that? I look around at my environment and I find this information. From this, I determine my current action. Should I slow down, speed up, stop the car? What should I do? All right? Then what you're going to do is you're going to perform actions creating one or more effects, right? An effect may alter, either your own state, such as movement, right? I push myself a little bit forward. Or it can do something like alter the state of the other, like I just rammed into another car, right? And that may alter that other car's state. All right? And at the end of the tick, what I'm going to do is I'm gathering all of these effects and I'm going to update the environment. And one of the things that games do is that all of these effects are processed simultaneously. Like the designers actually design the effects so that they can be processed simultaneously. This is what allows them to heavily leverage parallel processing. Because since it doesn't matter the order in which you process the effects, we can do them however we want. Right? So this is design technique that they do to leverage themselves. And in fact, what they do is they come up with these rules to combine effects independent of order. Like, so stackable effects are effects that are combined. So when you think about this as like position, okay? Like, if I walk forward, right, that causes me to have a certain position. But if somebody hits me at the same time, right, that also has me have another position. And what do I do in practice? I add those vectors together. It doesn't matter which order that I came up with that information. So I, as a designer, just say, oh, the effect for movement is add these vectors together. And I can do them in any order. All right? Now, one of the interesting things here to make this observation here is, by the way, we can model this with database tables if we wanted. Normally, when you think of a simulation, you go through and you process each agent one at a time, right? I sort of say, okay, you drive your car, and the other person goes and drives his car. Well, why don't I just sort of put all of the environment in one big table instead of processing each agent as in this loop? We'll process all of the cars at once as a single database query. I could do that, right? And then, by the way, what that means is that all those effects are just an update to the database table. That looks really cool, doesn't that? Except for that nobody actually wants to make their simulations in SQL. That would probably be annoying. But it's an interesting observation to make. All right. Oops, sorry. Okay. Now, by the way, some impacts of this observation, agents often perform a lot of similar computation, right? You've wired them to have roughly similar brains, and the only thing that differs in the agents is their observation of the environment around them, right? What matters is the data, not the computation itself, right? Well, if that's the case, maybe I should be able to do things to sort of share computation, to cut down a whole bunch of redundant processing. That'd be great if I could do that, right? Sometimes that's really easy to do. Sometimes it's a little more subtle. Back to, my sort of knights and skeletons example, right? I'm afraid of the skeletons that I see. The skeletons that I see here may be very different than the skeletons that you see here, right? So we have some overlapping computation that we can share in common, but not exactly the same stuff. All right. So the idea is that we have a basic programming pattern and that we're going to base everything around this. So I've elucidated some of this so far. The idea is we have this state effect pattern. Everything in your simulation, is all of the attributes of your agents are separated into states and effects. All right? So a state might be something like position, and an effect might be something like velocity. The way to think about this is that state attributes are read-only variables at the beginning, right? They're things that can't be changed until the next tick or the next simulation comes around. The only things that can be changed are effects. But as I said, I have rules to combine together effects independent of order. And this is what I'm going to leverage to do things like parallel processing and a whole bunch of optimizations here, right? So the idea is that velocity, right, because I said that velocity, the rule is that I do vector addition, right, by how you sort of push me, right? So I have some rule here for combining this independent of order, and this never changes at all within a tick. So a simulation tick now has three phases. A query phase where I read the state variables, an effect phase where I compute all the values for my effect variables, and then I combine them together with whatever rule you've told me to combine them together with. Wow, this starts to sound a little bit like MapReduce, doesn't it? Right? I read stuff, combine them together. Weird. And I have an update phase where I compute new values for state variables from the effects in the previous state variables. And I just define every simulation like that. Now I can do arbitrary computation in here, right? But the idea is that the way that I update the attributes of my objects has to go through this very well-defined process. How it is that you compute effects, arbitrary code, I don't care. All right? Now, the probability difficulty is the query phase. I want to process this like SQL. I want to take 30 years of database research, and stuff that we know, because look, it starts to sound like MapReduce too. I'd like to be able to take the technology that Google has created for MapReduce and pull it to bear on my simulation. But I don't want people programming in SQL, because that's just hard, right? And it's really hard to program agents at the individual level, right? So our solution is that we actually have a custom scripting language. And the language looks traditional or imperative, but it compiles using SQL technology. So this is something that we have, one of the reasons why you see a lot of game stuff on my slide is that this is a language that we've been showing to people in the games industry. We've also been showing it to people in the scientific industry as well, using it with things like animal behavior simulations and traffic simulations and the like. And a lot of the design points that we've made have been from feedback from people that we've been collaborating with. All right, we call it SGL because we couldn't think of any other name. The idea is that agents are defined individually. You create a script for each behavior. You assign a script to each agent, but they're processed as a batch. I suck them all together, and I basically create myself a custom data pipeline that I can program, then map to any architecture that I want. All right. In fact, it has very much an imperative syntax. It looks a lot like Java. In fact, I'm just going to... This right here is essentially my, let's see, that's a fish simulation for a biologist that we're working with here. This right here is part of a traffic simulation that we're working with a civil engineer on. So, in fact, the syntax coloring here is because I basically turned on Java syntax coloring, and it recognizes, my little editor recognizes it right away. So it's very, very close to what Java looks like. All right, but it has some restrictions to enforce the pattern. The state effect is encoded into your class definition, how the classes contact with one another. And by the way, I do have some limitations on iteration. So I don't have a standard for or a while, I just have a for each. That's my only limitation.
Is there a difference between loops in which the order matters versus loops in which the order doesn't matter?
Right now, this is actually a debate that we're having. Right now, we don't have any support for loops in which order matters. Right now, because the problem is that our goal has primarily been able to make it so that I can do a data flow pipeline for the entire program. To introduce things where loops matter, I would have to sort of take that loop and put it off to the side. It's not impossible. It hasn't been a priority for us, and we haven't. None of the people that we've talked to have needed it yet.
No,
so
obviously your parallelization is easier with loops.
That's right. That's exactly right. This really allows us just to go drill all the way down, right, with our parallelism. All right. So I have things like, everything has to be called either a state or effect. If I have a state, I have to have some sort of rule of how it is that I combine the states and effects in order to do the state here. I can either inline some sort of arithmetic expression, or if I wanted to, this could actually be a method call for some sort of some update function. And then, oh, by the way, all of the effects have to have some order-independent rule here. Unique is, I promise you this effect will only get one assignment, and I will throw some error if you lie to me. So, all right. So this is what a script looks like. I think what I want to point out here is that, so now, if you have any experience with sort of the types of data pipelines that SQL produces, this, by the way, is a relational algebra query plan generated by that script. And the idea is it's just feeding all of my agents through this data data pipeline, and at the end of the data pipeline is the result of the transformed agents for the next tick, is what I do. Right, so every single thing in this script corresponds to an element in the data pipeline. And as I was pointing out, it's key for being able to make this this conversion that I don't have arbitrary for loops, that I have to have these for each loops in order to be able to do this conversion. Right, and then now, as I said, this is great. Right, I can take 30 years of database research to bear here and do things like algebraic optimization. Like, this is the naive data pipeline that is created by this script, but oh wait, I have a bunch of rules, And I just transform it into this data pipeline. And by the way, the programmer of the simulation didn't bother with that at all. This was all done automatically. Yeah, that's right. Okay, I'll see what I can do here. Right, so that's one way in which I can get more efficient processing. Another way that I can optimize things is, well, let me just point out that in databases I also have things like indexing, right? And indexing is really key to get rid of the n-squared behavior, right? And there's all tons of database research on when do you automatically throw in an index and when is it useful. And once I've got the query plan from the scripts, I can do all that types of analysis and technology to automatically throw in those indices, right? And in fact, just looking, this was a prototype that we did for a simulation of sort of a battle simulation with sort of people fighting with one another using sort of our query plans and indexing techniques. This is if you just process the agents one at a time. But if I actually throw it into a query plan and index it, this is the behavior that I get. So this is an n-squared curve because everybody's interacting with everyone else. And this is the behavior that we get in our simulation. And, sorry. Right. And the thing to point out is I guess I didn't throw in this slide, is even if you're looking at animation frame rate, right, if you're looking at 60 frames a second, which is games are looking at, you get a 4-fold improvement. Suppose you're a scientist. You can live with 10 frames a second. Right? That's pretty good. You get a pretty good thing with that. That's an order of magnitude. Right here. Just by turning it into a query plan, mapping it down. All right. So, scientific simulations. So what I have here is that this is actually a simulation of fish. Please work. You're not working. There we go. So this is a simulation of fish, and this is written in SGL but without any of the indexing at all. The idea is that SGL is giving it its schooling behavior, and they're all moving off to the side here. If I do it with some indexing, right, that's noticeably faster there. Right, and all of this stuff was written in SGL. So what's the difference, by the way, in simulations, right? One of them is realism. Games cheat all the time, right? If it looks good, that's what matters. If you're a scientist, your model matters, right? You've got to have the right model. And this means much, much larger complexity, right? Number of agents. I think this should be swapped. Games are usually around 100 agents, and whereas in simulations are usually around 1,000 or so, right? So you need much, much better scalability for these types of things, right? Right. But, that's not too bad. The idea is also you want, otherwise it's mostly the same, right? You still want high-level programming, right, such that a scientist can program. And the idea is that we're going to use SGL as our simulation language, but you do want the performance, right? And in fact, that's okay, right, because we're going to be able to do everything in main memory, and we're going to compile directly into C++. And what's going to happen is that we're going to do things on the cluster. We're going to use MPI, but we're going to do all that for you. The only thing is that the scientist works in the scripting language, right? So I have automatic parallelization, and this is completely transparent to the programmer. By the way, right now, that fish simulation that you see, we're currently setting this up to run on Amazon's cloud, only because we don't have access to Microsoft's cloud yet to try things out. But look, running simulations in the cloud are great, right? You want to check out your model? Don't buy that cluster, right? Pay Amazon, pay Microsoft, right? To run it on the cloud and just get the services that you need, right? And all of this stuff is, we're just providing an infrastructure to map this thing onto the cloud so that you don't know. All right. So let me just mention that some of the things that we can give you when we're going into the cloud is, One of them is automatic partitioning, right? Suppose you're doing something like your fish, and the idea is that I want to map my fish automatically onto each node in the cluster. Scientist doesn't do that. I can automatically go into the script because of the state effect pattern, and I can look at things like, oh, you have some sort of range query there that tells me how I can split things up on the grid. And I will do it automatically for you. So you don't actually have to do the grid separation. It happens automatically. And it turns out that while this is hard to do in arbitrary programming languages, because of the limited interactions, right, both the order-independent loops and the state effect pattern, it's actually very, very easy in this scripting language for me to automatically figure out how to do this grid partitioning. Right? Fault tolerance is another thing that the state effect pattern makes really, really easy. Because since I have this well-defined communication cycle, I have very easy places to take checkpoints, which I can then immediately restart the simulation if I fail. Am I over time? Sorry. So I think I will, as I said, we have some stuff with traffic simulation, but I will leave it at